Hey, thank you everyone for joining today. My name is John Reynolds. I am a product manager at Aleo, and I specifically have focused on building digital identity products for Aleo. And my background is in computer science and cybersecurity. I also have a master's in software engineering, so I kind of span between the product and engineering realm. Today, I'm going to be talking to you specifically about building the antidote to the identity theft virus. And we're going to be discussing different emerging technologies that can help support making identity verification safer and more secure. So to kick things off, a startling statistic, 86% of consumers worldwide have been the victim of identity fraud. And this problem is continuing to get worse. It's approximated that around $50 billion was lost in 2022 as a result of identity fraud. And $28 billion of that was related specifically to identity fraud that was a result of information gathered from a data breach. To put that kind of abstract value into perspective, in the space exploration industry, NASA's annual budget is around $25 to $28 billion. So 1 year of identity fraud losses equates to 2 years of space exploration, apparently. These are the kind of headlines we continue to see. Some major centralized platform that has fallen victim to a data breach or a cyber attack, and user information has been exposed. I think everyone here in the audience would feel confident in saying a situation where either their information may have gotten exposed in some sort of brief, or someone they know's information got exposed. So at the end of the day, we can all really acknowledge that we have a big problem. And we can look back as far as the beginning of the internet to recognize that a unified identity layer never existed. And so some of these different tech companies and businesses were forced to build their own authentication systems in order to solve for the hard problem, which was to be able to identify who they were interacting with on the internet. Unfortunately, as a result of this variety of different custom authentication solutions, we fell into this world where we had a variety of different patchwork solutions. None of them were perfect, and none of them actually worked in all of the different contexts we needed them to work in. So when we think about this problem, the next step naturally is to think about why it hasn't been solved yet. And I think there's two interesting paths or directions or angles that you can take on answering this question. Why haven't we solved the identity problem of the internet? The first one is maybe a little bit more cynical, and that's to say that a lot of these platforms and companies, their incentives don't align with making identity verification more secure or more private. Because you see, these companies actually benefited immensely from some of the different transparency and visibility that they gained from users having less security or less privacy. And as a result, they've continued, I think, to slow down some of these aspects of the development of identity verification because the incentives just haven't been aligned. The other angle that you can take is this is a very challenging problem to solve. Identity exists in a lot of different contexts across the web, and depending on the situation where you're presenting personal information, there could be a need for higher levels of validation or lower levels of validation. So for instance, if I want to open a bank account, my bank is going to want to know more information about me, and they're going to want to be able to validate that information about me somehow. Whereas if I'm starting an account on a social platform, there may not be as much restrictions or validation required. So we've seen some progress in the identity realm, and when we're just talking about login, we can think of the example of SSO, single sign-on. And what this has done for us is it's shifted us from this patchwork of solutions where a variety of different third-party systems or companies are building their own authentication systems to a more federated approach where users can rely on existing systems or existing credentials to authenticate to a particular website or platform or service. So you can imagine the situation where you're trying to log on to some service and you use your Google credentials as opposed to that website spinning up their own personal or custom authentication system. And while this did help user convenience and it reduces some of the dispersion of user information across the web, ultimately, if you just look closely, you can tell that there's one major flaw here. And that flaw is the consistent dependence on a centralized entity. You see, even in the federated situation, where you're able to carry your credentials with you from one central platform to a variety of other third-party systems, the dependency is still on the central platform. And it continues to allow us to persist in this client-server model. This client-server model is where a server requests some information about the user submits that information, the server verifies it and stores this information, and that is the transactional requirements to go from being an unknown customer or user to being an identified customer with access to a particular service. And this model that we see here is what continues to get us into a lot of trouble. It's what ultimately ends up pushing a lot of information into the hands of centralized parties and makes it vulnerable as it sits on a server that is ready for attack, a honeypot, essentially. ZPass, which I'm going to be going into more detail about today, is a product that's built on top of Aleo. It's an identity product that leverages zero-knowledge proofs in the blockchain to provide more privacy and security to users. So like I mentioned, the three core tenets of ZPass are decentralization. And the goal of decentralization is to provide users more control over their information and their data. We want users to be able to define how much information they need to share and what context they're able to share that in. The next step to enabling a more meaningful identity verification process is privacy. We want users to be able to reduce the amount of information that they're forced to share without reducing the amount of validation or verification that comes with that data. And then finally, we want something that's trustless. We want platforms and users to feel confident providing their information to particular ZK programs and be able to execute those programs trustlessly, where the system cryptographically is able to prove and provide security and verification guarantees. So I think the way to reduce some of the complexities and very clearly show you what our goal is in the development of the product ZPass, I thought I would go through a few slides showing you visually how you can understand how ZKPs can change the dynamic and the transactional model of the web from a client-server model to a prover-verifier model leveraging zero-knowledge proofs. ZPass wants to move the dynamic where users are forced to share all of the information that you can see here on this ID card, an address, a name, expiration, date of birth. We want to reduce this to only requiring users to submit the minimal amount of information that would be required for some criteria that a platform or a service is requesting. So the goal would be to move from a paradigm where the user is presenting all of this data to reducing down to a situation where the user only has to present their date of birth. And a step further than this, ZKPs allow us to take the information and reduce it down to the predicate form, which is to say, instead of actually even having to expose your date of birth, you can just show or prove that you're over the age of 21. In this instance, the platform and service gets the cryptographic guarantees from the zero-knowledge proof that this information came from a trusted authority, that this information is valid according to the date of birth on the ID card, and no other information about the user has to be shared. So the user is protected, but also the platforms still have certainty and trust in the results that they're receiving. Again, this is what allows us to shift from the client-server model to a prover-verifier model. And that's to say that Rather than a user submitting their raw data to a server to be processed and stored, the user actually submits a proof to the server. And the server verifies that proof. And if the proof is verified, then access is granted. So we move away from the transactional model of giving servers and centralized entities our personal information and shift towards just proving the information that they need to know about us. This, fortunately, allows us or enables us to move towards a decentralized structure away from the federated structure. So it's one step closer to giving users full control of their information. And we're used to assimilating decentralization directly with the blockchain. And Aleo is a layer 1 blockchain. But we're also used to assimilating public or transparent or visible with blockchains. And the main difference between Aleo and the traditional blockchain is that Aleo actually is a private blockchain. So the information on Aleo is encrypted. And using zero-knowledge proofs, users are able to prove information about themselves or about the information that they possess on chain. And no other users can go to an explorer and see all of the raw data. It's completely encrypted, and it is also decentralized because it exists on a ledger. And so in this scope, you can imagine that a user now has the ability to rely on ledger-based technology to support trust, but then they also get to leverage zero-knowledge proofs to enhance the privacy of the transactions that are taking place on the blockchain. So the way that this works, or the way that you can think about this working on Aleo, is through a series of events. You start with a program or a smart contract, you can imagine it as, that exists on chain. A user pulls that information off of the blockchain, off of a program registry, and they execute that program off-chain. This is an essential piece to understand here. The portion that's providing the privacy and that's enabling the zero-knowledge technology to really shine is that the user is able to execute these programs on their local machine or in a secure environment. They're able to produce a proof from that execution off-chain, and then the user sends or broadcasts that proof to a validator. And a validator node is able to verify the proof and then update the state of the blockchain. So as this diagram shows, again, we have a program, and within the program, there's different functions, or transitions as we call them at Aleo. These get executed, and these update ultimately, when finalized on chain, the state of the blockchain. But first we go through the execution process off chain, produce the proof, and then the user has the ability to broadcast that to the chain or even verify that proof in an off-chain capacity entirely. So when we think about ZPass, or this identity product that I've been discussing, we start by creating a ZPass. The creation of a ZPass, or the issuance of the ZPass, is a process where the data about somebody is created into a digital credential or a digital ID, and then a signature is added over the information for that particular credential. ZPass also actually supports transitioning any sort of signed ID document into a digital credential. One example that you'll see in the diagram that I show here shortly is using a passport for the example. So many people might not know this, but passports actually have NFC chips in them, so they can be scanned by any standard iPhone. And each passport has all of the information relevant to the passport and the passport owner existing within this NFC chip. It's also all hashed into a Merkle tree and digitally signed. And what this means is we could scan a passport, we can extract the data elements from the passport, we can hash those elements and verify the signature against the publicly available signature of the signing authority, which might be a government or the authorities that the government of a particular nation have assigned to issue their passports. And again, these are public keys or public addresses that can be collected or that are publicly available. So the point that I'm trying to make here is the creation of a ZPass can be something that's from a net zero starting point, or it can be something that exists from a little bit further along the line where we're using existing credentials that are already accepted in real-world scenarios, such as a passport. The next step, once you have that information and that data into a credential, you generate a proof. And generating a proof is the response to some verification. So the user has a credential, they're answering some verification, saying they're over some age or they're from some particular country, and a proof about that information is generated. And then finally, the user has the ability to show that proof. They show the proof to a platform, the platform verifies the proof, and the user is able to progress through the flow. So to go into a little bit more detail about the creation process, again, you can imagine starting with an ID, like a passport. And this would be going from a passport, from a physical credential, to a digital representation of that credential on chain. So you start with the passport, and then in the middle section here, you see we have an execution. A signature verification would be the first part of the process for this execution. And that's to say that the goal here to create a ZPass or to create a record on chain is to simply verify that the information from the ID is valid according to the signature and the issuer's public key that is relevant to that ID. Once you verify the signature, you can add the attributes of that credential to a record on chain, and then you additionally have a proof that tells you this information came from a signed credential for this particular issuer. And so the proof tells you that it's valid according to the signature, and the record possesses the actual data for you to use in a future capacity to verify some information about yourself. So we can assume at this point we now have a ZPass credential, a record and a proof on chain. Now, the benefit is that users can reuse this in multiple capacities. They can use this across a variety of different contexts, and they can scale the amount of information up or down depending on what the service or the platform requires. So from this point, again, it's a similar structure where you have some data element, you have an execution, and then you have a result. The ZPass, in the form of the record, is presented to an additional program. And within this program, the execution is responsible for the claim verification. So for this, we'll just continue to stick with the over the age of 21 as the example. So the ZPass has the user's information, and it's encrypted, but it exists on chain. The user presents this record to another execution that checks if their date of birth equates to them being over the age of 21 based on what the current date is. Also, likely it checks that the passport that's being presented or the record that's being presented is not expired. And then finally, it provides you the proof as the result. And the proof attests to the fact that the user's information met the verification request, which is that they're over 21 and they have presented a valid passport or a valid ZPass ID. And then finally, like I've mentioned now a couple of times, the proof for it to be verified can be sent to the Aleo blockchain in the form of a transaction where a validator node will receive the proof and that transaction and verify that the proof is valid before they update the state of the blockchain. Or it can be verified off-chain, where the user just presents the execution from the blockchain, and the platform verifies the proof that the user provides back, and maybe they also verify that the ID that the user presented, the ZPass the user presented, does in fact exist on chain. So they could do a zero-knowledge proof, an inclusion proof that proves that this particular record was issued on chain. And you can do that by checking the global state root. So I'm going to get a little bit more granular with this example as we move towards a more code-focused version of this explanation. So this is going to be very similar to what I just explained, but we're going to go into a little bit more granularity. We'll start with the issuance portion. And as you can see, the idea of the issuance is taking either an existing credential and converting it to a record on chain, or it's taking new information and issuing it in this format so that a user can receive this and have a representation of it on chain. So to begin with, you want to switch from just having issuer public key and then attribute as an example here to actual variables or actual attributes about the user. So we can assume issuer public key, owner, date of birth, nationality, expiration, and a signature. Now that we have this information, the next step, if we're actually going to be issuing this credential, is we go through the process of converting it into a Merkle tree. The reason that we do this is we want to provide the ability for the user to have the most privacy and security. While we do support a credential schema approach in instances where it makes more sense or it's more computationally viable, in the example I'm going to be covering today, I'm going to be discussing the Merkle tree approach that we use. And despite the fact that Aleo has a completely encrypted blockchain, there are still situations where information might be private or delicate enough that even in an encrypted form, you don't want to present the information on chain. And so instead of doing that, what you can do is you can leverage a Merkle tree. And what a Merkle tree does is it separates the attributes out into a set of hashes. So you can see on the slide here, we have owner, date of birth, nationality, and expiration separated across the top. The first step of generating a Merkle tree is hashing those first attributes. So you create a hash, and for those who aren't familiar with hash functions, the purpose of a hash is to create a representation of some set of data that can't be converted or decrypted or deciphered back to the original set of data without knowing it. And so the difference is for encryption, when you encrypt something, you have a private key that you can use specifically yourself to decrypt it. A hash is different. You can't go backwards from a hash in the form of a function. So it's a one-way function. It's just creating a string representation of some information. So you hash these different attributes, and then the next step is actually combining the hash of these different attributes in the format of a tree. So you can see we start with the variety of these hashes, then the next step is hashing the combination on each side of the tree, and then finally, in this example, we just have 4 attributes. These converge specifically to a root hash. And that root hash is a representation of all of the attributes within the credential. And this root hash is what the signature is generated around. So if I'm going to some service provider, or if I'm going to some platform or business, and they're going to issue me a credential, they'll receive this information about me, and then they'll have an automated flow to reduce this down to a root hash and then sign it with their public or with their private key. That can then be verified using their public key. So in the future, everyone is aware who provided the credential and that none of the information or attributes within the credential have been disturbed. The next really convenient thing about using a Merkle tree approach is that it allows us to selectively choose different attributes to prove during the zero-knowledge program portion. So without having to actually have any of the information exist on-chain outside of the hash version of it, what we can do in a zero-knowledge program is we can say, for instance, we want to prove that a particular date of birth equates to the user being over some age. So we can identify the date of birth, and in order to prove that we know the date of birth that is on the credential, we can create a proof that says, or that executes a function that takes a raw date of birth, so a plain text date of birth, and this function executes locally, so there's no way for this information to get dispersed to the service provider or to the platform. And we can say, I can prove to you that this date of birth is the date of birth that exists within this Merkle tree, which is signed from a particular issuer. And the way that you do that is you take the date of birth, you hash the date of birth, you combine that hash with the hash of the owner address to produce this path, and then you combine these two hashes to produce the root hash. So what you've just done essentially is you have produced the root hash from a raw date of birth value that isn't expressed in the credential itself. So if you're actually able to produce the root hash and the signature is verified, then you can validate that you knew the date of birth that equated to this specific root hash. So once we've gone through the process of a signature verification within a ZK program by, again, reducing a particular attribute to the hash, combining those to produce the root hash, and then verifying the signature associated with the credential, we go to the next step, because after this has occurred, we can assume that a ZPass has been issued and the user possesses a record and a proof. So we take all of the attributes that were presented and then converted into a Merkle tree into the record that exists on chain. So now on chain, there is a credential representation that contains the issuer's address, it contains the leaf hashes for the Merkle tree, and it contains the root hash and a signature. All of this is encrypted on chain and can only be decrypted or viewed by the owner, which is to say the person with the private key that owns this particular record on chain. The next step is verification. And here I have 3 different verifications that we could assume could be requested. The first one is checking if the age is over 18. The second one is checking if the user is a US citizen. And the third one is checking if the credential is expired. Once the user has completed all of these verifications, the result is a true or false output response and a proof. If the result is true, it means that the user passed these verifications, and the proof attests to the fact that the user presented a valid credential that was verified, and the information from that particular credential is what was used to verify these different claims. This means that the user is able to prove to a platform that they are over the age of 18, they are a US citizen, and that the credential they presented is not expired, without exposing any additional information whatsoever. Now I'm going to go into some more code demo, but before I do that, I'd like to just go into a little bit more explanation about Aleo and the structure of Aleo and how it works. So I'm going to return to an earlier slide. This slide here, which shows the essence of off-chain execution, which was one of the main tenets of Aleo network. So just to run things back a little bit, as I describe Aleo, Aleo network, again, is a layer 1 blockchain, and it allows you to develop zero-knowledge applications on-chain that execute off-chain and then maintain state on-chain. And there's a few different systems that Aleo has developed to make it a lot easier for developers and builders to begin leveraging zero-knowledge proofs and build applications that can leverage zero-knowledge proofs. So to start with, one of the things that's super important to recognize is that not any program can just be run to generate a zero-knowledge proof. The idea behind zero-knowledge programs is they exist as a system of equations. And so you have to be able to reduce some program all the way down to a system of equations that's structured in a way that has the ability to receive private inputs, execute functions to produce execution transcripts and proofs that can then be verified. So one of the ways that Aleo supports the developer in this focus is we've created a high-level language called Leo. And what Leo does is Leo compiles down to Aleo instructions. Aleo instructions is a lower-level language that is then used to synthesize rank 1 constraint system, which is the system of equations that allows you to generate and verify zero-knowledge proofs. Usually, you have to be pretty confident and comfortable with circuit language and understanding the deep levels of zero-knowledge cryptography and proofs to build and develop applications in this landscape. But Leo has made it a lot easier to build and develop in a JavaScript type syntax and have zero-knowledge proof or zero-knowledge programs as the result. So once you have this, this is what enables you to execute the program to produce proofs. So this is the workflow that, as a developer, you can get very used to on Aleo. The program is executed off-chain, a proof is produced, and that is then, again, broadcasted to some validator node that verifies the proof and then updates the state of the blockchain. So I'll go ahead and switch over now to some of the Leo code that I want to talk through so everyone listening can realize just how easy it is to build zero-knowledge applications using Leo and in the Aleo environment. So just to start off with, one of the things that is important to recognize in the Leo model and in Aleo is that we refer to transitions we refer to functions as transitions. Transitions are functions that can receive records, or they can receive state-containing data objects that exist on Aleo, and they can execute functions around that information. And then they can also produce records on Aleo. And Aleo is similar to Bitcoin as it relates to the UTXO model. So Aleo has records which are similar to a UTXO, or an unspent transaction, for those who are familiar with the Bitcoin structure. And the idea is that a UTXO, or an unspent transaction, or a record, can only be spent once. And so if you have a set of information, or if you have a record on Aleo and you present it as an input to a program, the program will actually consume that record. And then the developer of that particular program can decide if it wants to reproduce the record that it's consuming, or if it does not want to do that. But it's just important to recognize that transitions are the responsible functions for receiving the input of those records, deciding on consuming it, and then either reproducing a record for the user or not. So in our case, once we're at this point, we can assume that a user has a digital ID. They have a credential now. And what they're providing as an input to this transition function is a signature and then a credential. And at the top here, I've very simply defined what the structure of a credential might look like. In this case, again, issuer, leaf hashes, an expiration date. And then at the bottom here, we have an additional data object, which is the credentials ciphertext. And this is just an additional feature that we can tag on to the end of the struct of a credential that has an encrypted version of the hashed leaves in case we want to give the user a little bit more flexibility in understanding the information that exists within the credential. But in the most privacy-preserving way, this wouldn't necessarily be included. So a user presents a signature and their credential. And once that's presented, the transition function here says that it actually produces a signed credential, which is a record on Aleo. So this transition function is not receiving a record, it's just producing records. It's receiving a credential structure, and it's receiving a signature. And as we step through this function, we see that the goal of this function is to first identify that the person calling the function is actually the subject of the credential, or the owner of the credential, because we want to make sure that the users who are trying to claim some on-chain representation of this are the people who actually own the information, or who the information is about. The next step is checking the expiration. Again, this is as simple as making a comparison to the current date against an expiration value that exists on the credential. And then finally, the final step here is computing the root hash from the leaf hashes. So even though a root hash might exist within the credential, it's still essential to compute the root hash, because that's what the signature is verified around, to ensure that there hasn't been a situation where the credential has leaf hashes that are not representative of what the root hash is representing itself. And finally, we go through the signature verification step. So since we've computed the root hash from the leaf hashes, we have the signature and we have the issuer address. That's all that we need. Those are the three variables needed to verify a signature. Once we have a successful signature verification, we can return a signed credential to the user. And the user will receive this record. If we execute and broadcast to the blockchain, they'll receive this record on chain, and within that particular transaction, there will be an execution proof that represents proof that the information the user presented is valid and that the signature was verified. So I'll quickly run this so you can see what the outputs look like. Okay, so maybe I'll start by showing the inputs here so it's very clear. So again, like I described earlier, signature is presented, and here's what a credential might look like. And if we take a look here at the bottom of the screen, we can see what an output looks like. And again, an output is a record that exists on chain. So the output now has formed a credential in the form of a record on chain. We have an owner address that is included. We have an issuer address. We have an array of leaf hashes. Then we have an expiration date. Now the user possesses this credential on chain, and they can use it to verify themselves in different contexts. I'm going to go ahead and show you what the verification process looks like as well, so you can get a feel for just how simple this is. But again, I just want to be clear here. This is how straightforward developing using Leo can be. And at the end of the execution of this function, a proof is generated, and that proof can be verified in a variety of different contexts, or it can be sent to the blockchain. When we look at the verification side, so we have a verified date of birth. This function verifies that a date of birth is equivalent to a date of birth that exists on an ID. And then we also have verify nationality. And then finally, verify age condition. And verify age condition is the function that's responsible for actually verifying that a user is over some particular age, like over the age of 21. So I'll step through this quickly. Verify age condition accepts a record, and that is in the form of a signed credential, or a ZPass. They accept a date of birth, an age, so this would be the age that you're trying to prove that you're older than, a current date, a condition, so I guess you could be proving older than, less than, or older than and equal to, less than or equal to, and so the condition value is what allows you to define that. And then an algorithm Boolean, and this is just in the case that a different hash function was used, we have a flag set to say that the hash function for this particular example was using Poseidon. So when we step through this, once again, we do an assert to ensure that the individual calling the function and presenting a record is in fact the owner of that record. On chain, there should be no way that it's even possible to present a record that you are not the owner of, since you won't be able to decrypt the record unless you're the owner of it. The next check is producing the Merkle tree and defining the path to the date of birth within the Merkle tree. Then we verify that the date of birth field is valid. So we check that the date of birth matches the date of birth, the hash of the date of birth that's provided matches the hashed date of birth that exists within the credential. And we continue through these steps of parsing out the date of birth, turning it into a Unix value, subtracting it from the current year, and then ultimately making a comparison against the value that we are able to calculate and the age that we're trying to check against. And one of the exciting things about zero-knowledge proofs is they have the ability to provide a lot of privacy preservation, but they also allow us to provide guarantees around how functions or programs are being executed. So when you look at this and you see the result that's produced and you see the inputs that it requires, you can be confident that if the proof is valid and can be verified at the end, that the execution that occurred is exactly what's represented in this function here. And it is down to the level of specificity of this particular program, since this program exists on chain. So we can be certain that the proof produced came from this program. We can relate it back to this program, and we can be certain that any results or state changes that occur came from this program as it relates to the outputs and the proofs. So once we've gone through the different verifications of age, we've selected the condition, and we've proven that the user has passed this particular verification, then the result is just true or false, and the proof can be used to verify that. So I'll go ahead and execute that function now so everyone can see just how quickly this operates and runs. So I've copied over the relevant information. It's a credential structure here. I've presented the different inputs that I've described earlier. And when I run this, you see it executes the program and it provides a response of true. Now this is just one portion of the development process on Aleo. So of course, this is a great way to test by executing off-chain, by running through different test cases and examples, and by walking through to make sure you're getting the results that you would expect. But the next portion is creating an environment where a user can actually interact with this program in a privacy-preserving way. And one way that we've been doing that at Aleo is by expanding on the level of support that we're providing to solutions like WASM. And what that does is this allows users to execute functions from their browser client-side. And the important part about being able to execute programs client-side as it relates to zero-knowledge proofs is it means that you can provide the inputs on your local machine so that you can ensure that they're not getting sent or distributed to third parties or centralized entities. And once you've executed that program, which can be completely disconnected from the internet, you're going to produce a result saying true or false maybe, or maybe saying some public value, and a proof. But because you executed it locally and you're just sharing the result and the proof with these other services, there's no way for that information or data to get exposed. So WASM, Rust and WASM, WebAssembly, allows us to create a safe sandboxed environment within the browser where a user can provide information to programs and functions that can be executed to produce proofs, which then can be verified in a trustless and privacy-preserving manner. That is everything in terms of the discussion and demo for today. I still have about 15 minutes, so if there are any questions that are more technical, or even if you have a high-level question around zero-knowledge proofs or Aleo, please feel free to come down to the table, I guess, and grab a mic and ask your question, and I'll do my best to give you an answer. Yeah. Yeah.
Can you hear me better? All right. You said Aleo is a private blockchain. In my mind, that means there's no decentralized group of validators or anyone securing the chain. It's one organization, person controlling who can censor and whatnot. Is that the case with Aleo, or are you saying private because all the information is encrypted?
Can you say that one more time, just the beginning portion?
Yeah, when you said Aleo is a private blockchain, in my mind, the differentiator between private and public blockchains is who can validate transactions on the chain. So a private blockchain means it's permissioned. Only one entity can validate transactions on the chain, as opposed to a public. But you also said it's encrypted, so I just want to make sure I'm understanding.
Yeah, so Aleo is a layer 1 blockchain solution. It is decentralized, and it is privacy preserving, as in the essence that every transaction that is broadcast to a validator on the network is done by generating a zero knowledge proof and then providing that in the form of a transaction to a validator node. And a validator node is able to verify that proof and then update state accordingly. And so it is public and permissionless in the sense that a variety of different validator nodes can validate transactions to update state. But it is private in the sense that any state information that exists on chain is encrypted by the private key of the owner of that particular address. And then also on top of that, information and transactions that are sent to validator nodes are done so in the form of a zero knowledge proof instead of the plain text information. So they just have to validate the proof instead of re-executing all of the information like what is done on Ethereum, for example.
Perfect. Really helpful. Thank you.
Yeah. Great question. And for anyone who didn't hear that last question, the question was, if Aleo is or in my statement earlier saying that Aleo was a private blockchain, he asked for some more specificity around how interactions with validators worked and what I was acknowledging as the difference between public and private.
Hello. What are the use cases that you guys are targeting now? And being a layer 1, with the multi-chain thesis and layer 2s, how will proofs interact with the rest of the ecosystem?
Okay, just to repeat what you're asking. Are you asking what are some of the other use cases as it relates to zero knowledge proofs that we've seen, and how and what is our role in the larger ecosystem as a layer 1 solution?
Yeah, I think specifically for Aleo, what are the use cases that you guys are targeting with your zero knowledge proofs, and then how does that play into the greater ecosystem? Perfect.
Yeah. So I think the use cases that we have leaned into a lot have been identity use cases specifically. We've put a lot of focus into this ZPass product to try and establish different opportunities to expand from this protocol and infrastructure across different business use cases. So you can, we all were very familiar during COVID, the process of going to get a vaccine and then showing someone your vaccine card. I think the medical field has a lot of opportunities for better enabling users to own and share and express things about their medical history in different instances, like to insurance companies or to, for school to gain access or to admission, right? You have to prove you've completed some vaccinations. I think in a lot of these instances, we're forced to overshare, that one in particular, where we could enable users to better protect their information and have a bit more control over it. We've also done a fair amount of research into university structures, so universities that have different credentials and information, diplomas, focuses of study, and how we can enable users to better leverage some of that information. And then from the finance space, we have KYC, proving different information about your financial history, proving that you might have some amount of funds in an account to provide proof of funds. And then we've also looked at how the impact of zero knowledge proofs can help enable a more trusted and reliable AI model. So we've talked a fair amount about ZKML and this idea of ensuring that the results that users are receiving are from a particular model that they have either paid for or that they are relying on. And I think that has a lot of opportunity to grow and impact the AI and machine learning space pretty dramatically as well. So ideally, we're trying to foster an ecosystem and a community of developers to be able to think through more unique and creative ideas to leverage this technology. But we've tried to reduce the amount of effort and workload that it requires to get from 0 to 1 in using zero-knowledge proofs and implementing them into traditional applications. Hopefully that helps. Yeah, sorry, you're gonna have to come down.
Hello. Thank you for your presentations, important subjective. And you told about the verification, the equation about the how to validate. I have a question. If I have my ZPass and participate to some DAOs, like I have my passport and I participate like the customs officer DAO, the alcohol markets DAO, and these DAOs validate if I have 21 or older age. The custom officer validate if I am a US citizen or if I am a Brazilian. So I would like to understand how can I have my ZPass and participate to specific DAOs to validate private informations about me. If you can connect the zero-knowledge proof with DAOs to specific subjections, like, oh, this is the custom officer DAO. If you participate to this DAO, they will check if you are a US citizen or not. You permit participate to this DAO. If you participate to the alcoholic markets DAO, they will check if you have 21, 22 years old. So not assign smart contracts and participate to DAOs to validate these zero-knowledge proof informations.
Great question. So the question was, there's a variety of different DAOs that may need to verify some information related to the organization that they're supporting or the entity or the vision that they're supporting. So there could be a alcohol-focused DAO where it needs to verify that users are over the age of 21. And how can we use ZPass to enable that through zero-knowledge proofs to minimize the amount of information that's being shared publicly or transparently? So great question. So to start off with, the first portion and the majority of what I just described is mostly focused on the user experience and enabling users to gain the ZPass itself. The next step to that is actually enabling platforms to verify. So users produce the proof and platforms verify the proof. So we also have built out a SDK and an API to support ZPass. It is not public right now, but we plan to release that this year. And the goal will be to give different platforms and services, such as a DAO, the ability to very easily integrate with the ZPass API so that they can either receive the proof, the execution proof directly from the users who are trying to prove information about themselves. So the user would have a ZPass produce the proof, and then they present that execution proof to the DAO, and the DAO can verify that using the API, or the user actually submits that verification on-chain, which produces a transaction ID, and that transaction ID can be provided to the DAO, and they can verify that the transaction was executed by your address using the API as well. and they see the result then. And since validators natively verify proofs, in that case, the DAO actually doesn't even need to run the proof verification. Instead, if the transaction exists on chain and it's been validated and is finalized, then we know that we can trust the proof, because every single transaction has to have the respective proof validated before it's finalized on chain. So I guess the short answer to your question is, there will be an integration to support different platforms, such as DAOs, to leverage this technology for their users as well.
My idea, because DAOs is like, imagine alcoholic markets. Maybe I'm use my point of view. I buy something in city market. So city market is the first member of the DAO, and I allow the alcoholic DAO to check my information, and after maybe Walmart participates to this DAO. So I'm a member of this DAO. So I don't need to know if Walmart, City Market, Target, who market will check this information. I need to know the white paper of the DAO, and this DAO can check my information. So my vision about the DAO is integrate all markets, all kind of companies in one place where they can participate, and I validate the DAO. So in the future, we need to know your age, and we need to know like your physical body, so the DAO will discuss with the integrants and all participants to the DAO to restructure the DAO and check the validation of the participants. So I imagine the DAO, a lot of companies to participate, integrate, and take discussions with all markets and the participants too.
Absolutely, absolutely. Okay, it looks like that's all the questions for today. Thank you so much for the time. I appreciate everyone listening in, and please feel free to check out ZPass at zpass.aleo.org, or check out just Aleo in general at aleo.org. And you can also find me on Twitter at snarkworld. So appreciate the time today. Thank you so much, and have a great day.